Hey, this is Horner. We're going to look at the problems for electromagnetic waves. So the very first problem here says, what is the electric field amplitude of an electromagnetic wave whose magnetic field amplitude is 2 milliteslas? So we remember that if I know the electric field and I divide that by the magnitude of the amplitude of the magnetic field, that should be equal to the speed of light. So let's just rearrange the equation for the magnitude of the amplitude of the electric field, and that should be equal to c, the speed of light, times the amplitude of the magnetic field. Speed of light is 3 times 10 to the 8th meters per second, and we know that this one is 2 times 10 to the negative third teslas. So when you multiply the two together, you should get an electric field strength of 6.0 times 10 to the fifth, and then remember electric field is measured in volts per meter. So a pretty simple problem as long as you know that relationship from the lecture that we did earlier. Next problem says, what is the magnetic field amplitude of an electromagnetic wave whose electric field amplitude is 10 volts per meter? So we already set up the equation earlier. Now we're going to solve it for the magnetic field strength. That's equal to the electric field strength divided by the speed of light. Our electric field strength here is 10 volts per meter. We know the speed of light is 3 times 10 to the 8th meters per second. And so we will end up here with an answer of 3.3 times 10 to the negative 8th volts times a second over a meter squared, which is actually a Tesla. So this is ending up being 3.3 times 10 to the negative 8th Tesla. So it's really small. That's about 1/1000th of the magnetic field of the Earth. Let's go ahead and take a look at the next one. A microwave oven operates at 2.4 gigahertz with an intensity inside the oven of 2,500 watts for every square meter. So they want to know what is the amplitude of the oscillating electric field. Okay, so we're actually looking for E0 here, or E naught. We know that our equation here is the EO value should be equal to 2 times the intensity all over the speed of light times that electric field, and we need to do this to the square root. If we end up doing that, we're going to do 2 times our intensity, and our intensity here is 2,500 watts per meter squared. We're going to divide that by 3 times 10 to the, oops, this is epsilon not, 3 times 10 to the 8th meters per second squared, and then we have 8.85 times 10 to the negative 12th, and that is our epsilon naught value for the permeability. And then this ends up being 1.4, oops, sorry, that should be, so used to writing the speed of light, 1.37 times 10 to the third volts per meter. So that's our equation. Remember, it comes from the intensity. The intensity here is equal to C times epsilon naught times E squared, all divided by 2. So we've just rearranged that equation. Let's go ahead and look at the next part. So now they want to know what is the amplitude of the oscillating magnetic field. So our magnetic field here we know is related to the electric field by magnetic field amplitude is the electric field amplitude divided by the speed of light. So this one's a lot easier, 1.37 times 10 to the third volts per meter. That's the third volts per meter divided the speed of light, which is 3 times 10 to the 8th meters per second. And so you end up with a value of 4.6 times 10 to the negative 6th, and then that is a Tesla. Both those values were pretty reasonable for what we're doing. Next problem that we have here says the maximum allowed leakage of microwave radiation. That's kind of scary. From a microwave oven is about 5 milliwatts per square centimeter. If the microwave radiation outside has reached this maximum value, what is the amplitude of the oscillating electric field? So here we go again. The intensity is equal to the speed of light times epsilon naught times E squared, EO squared, all over 2. So here we know that if I have 5 milliwatts per centimeter squared, I need to get that one into watts per square meter. So to do that, here's what I'm going to need to do. I know that there are 100 centimeters in 1 meter, but I want to go to meters squared, so I have to square both the 100, the centimeters, the 1, and the meter squared. If you don't square everything, if I just did 100 centimeters squared over 1 meter squared, it would not give me the right answer. So this one is going to be 5 times 10 to the negative 7th watts per meter squared. Now I have my intensity in the right value. So we want to solve for the electric field. So that's equal to the square root of 2 times I all over C times our value here, epsilon naught. So this is going to be equal to the square root, I always have to do this long, of 2 times 5 times 10. This is a 5 times 10 negative 7th. And we're going to divide that by the speed of light, which is 3 times 10 to the 8th, times our value for our constant, which is 8.85 times 10 to the negative 12th. So if you do that, you should end up with about 0.019, and that would be volts per meter. And that's a pretty small intensity. So because it's such a small intensity, we should have a very small electric field on the outside. All right, let's go ahead and take a look at the next one. This is number 5. It says, at what distance from a 10 milliwatt point source of electromagnetic waves is the electric field amplitude 0.01 volts per meter? So here we've got, this is 10 milliwatts. We could then go through and here's our 0.01 volts per meter. So I know that I'm dealing with intensity. Intensity is equal to power, so that's why we're using milliwatts here, over 4 pi r squared. And that is actually also equal to, if we remember, C times epsilon naught times our E value, our intensity, all divided by 2. So if I take this equation right here, so what I've got boxed, if I take this and let's solve it for R, my R then is going to be equal to the square root of 2 times P over 4 pi times C times epsilon naught times our amplitude of our electric field squared. So now we've got to get everything in the equation. So this would be 2 times, now this is 10 times 10 to the negative 3rd watts because it's 10 milliwatts. Then we're going to divide by 4 pi. Then we've got speed of light, 3 times 10 to the 8th times our constant value, 8.85 times 10 to the negative 12th. And then we need to multiply that by our electric field strength, which is 0.01. Now that we've done that, you do all that math, you should get 77 meters. So greater distances do result in much smaller electric fields, so that's really what we should expect it to look like. Very last problem here says a radio receiver can detect signals with an electric field amplitudes as small as 300 microvolts per meter. They want to know what is the intensity, the smallest detectable signal. So here we go. Intensity here is just equal to the speed of light times our constant value times the square of the electric field amplitude divided by 2. And that's going to be equal to 3 times 10 to the 8th times 8.85 times 10 to the negative 12th and then we need to multiply that times 300 times 10 to the negative sixth squared. So that's that 300 microvolts per meter, and then we divide that all by 2, and you should end up with 1.2 times 10 to the negative 10th, 10 to the negative 10th watts per square meter. So that's really a very, very small signal, and that should be picked up by an antenna system that has been amplified. So there's our intensity, and that is it.